Hello friends. So, we have been discussing in the earlier lecture that various processes that act on for the natural purification of the waste, particularly the organic waste and some sediment entered in the river with the wastewater discharge. So, this lecture we will be elaborating further on how this processes affects the DO and BOD in the river, how this timeline of DO and BOD changes within the river. So, if we see the different zones of pollution in a river stream, particularly when it is receiving a waste stream. Okay. So, what happens post that point? Now, typically there are 4 different type of zones which can be considered in a river when it is receiving a sewage discharge or wastewater discharge, right. So, these 4 zones are the clean zone, decomposition zone, septic zone and recovery zone, right. The clean zone that you are seeing here, that is you can say that either first zone or maybe the last zone also. So, what happens that the river is initially, let us presume that river is initially clean. So, in its natural state, okay, there is a good amount of dissolved oxygen. So, let us say this is the black line you see is the dissolved oxygen level. So, there is a good amount of dissolved oxygen and this dissolved oxygen is near its saturation value, okay. So, near saturation value of the dissolved oxygen is there. There are fishes, there are aquatic organisms, okay. There are some smaller creatures at the bed or bottom of this. So, that kind of condition is there. Now, what happens that when a waste is introduced in the river, a waste stream comes introduced in the river, then the first zone that we get means immediately after introduction of this waste stream, that we call it decomposition zone, okay, when this decomposition of the waste starts. So, initially you see the BOD is very low, okay, let us say for say this is the background value, okay, any background value you can take it, okay, but often very low value, okay, around maybe 10, 5, 4 whatsoever you take. Then when waste stream comes and it gets mixed with the river water, so the BOD value of the river water shoots up, because your waste is going to have a very high BOD value, and as we discussed that there is going to be the dilution happen. So, because of this dilution factor, this BOD shoots up, okay. So, for say your initial BOD is let us say 5 milligram per liter and flow rate is 2 meter cube per second. So, total mass introduced from here is from 10, while your waste stream which is coming in having a flow rate of 0.2 meter cube per second and a BOD value of say 500. Okay. So, how much this becomes? This becomes 100. Okay. So, total as we discussed in the previous lecture, if you try to figure out the total concentration here. So, total mass is 10 plus 100 divided by total flow is 2.2. Okay. So, that is 110 by 2.2. which is close to 45 or that way. Okay. So, from 5 it has shooted up here. Okay. Now, what happens that at this particular point BOD is very high, the dissolved oxygen is adequate. So, the microorganisms start degrading or decomposing the organic matter present in the water. So, you will see that the decay of BOD starts, okay, because of primarily the biodegradation process, primarily it is the microorganisms. So, these microorganisms will actually start decomposing organic matter, and for the purpose they will consume oxygen. It is generally aerobic microorganism. So, they need oxygen for converting organic matter or decomposing organic matter. So, in the process they will consume oxygen, and what will happen, what eventually will happen, that the level of oxygen, if you see here. So, this was your BOD, and BOD will start decreasing slowly, while there is going to be a rapid fall in the oxygen level, because this oxygen is getting consumed for the degradation or decomposition of organic matter. Oxygen is not only getting consumed, oxygen is coming from the atmosphere also. So, there is a oxygen transfer is still taking place at its standard rate. So, there is a oxygen transfer, but the rate of decomposition here, or the net rate of decomposition here, net rate of oxygen depletion here is much higher than the rate of oxygen coming in the system or rate of re-aeration, and that is why the net oxygen level starts falling, and so is the net BOD, because the amount of organic matter is getting decomposed, and as a result BOD also start decreasing. So, this once this process starts, the kind of like fishes and this thing, it becomes difficult for them to survive. Still some of them can survive, but it increasingly become difficult because oxygen level is falling, and then we enter to the septic zone, where the dissolved oxygen or DO reaches its minimum. So, this is the minimum dissolved oxygen. Let us say it has come down, most of the oxygen has depleted in consumption of the organic matter, and since the oxygen supply has fallen rapidly, there will not be any fishes in here, there will be only some sludge worms and mosquito larvae present in the water. Okay. Some midges and these kind of things could also be there. While in this zone also your BOD or whatsoever organic matter present keeps on decreasing. What happens that since the BOD level is falling, the requirement of oxygen for further degradation also starts decreasing. Okay. So, now since the requirement of oxygen or the oxygen uptake for the BOD decomposition starts falling, and your re-aeration is still taking at that place. So, you comes a point where this is almost equal, and then once the further BOD decreases, your the consumption rate of the BOD consumption rate of the DO becomes smaller as opposed to the re-aeration rate. So, the amount of dissolved oxygen which is coming in the water exceeds this rate, and as a result this dissolved oxygen again starts building up. So, the dissolved oxygen concentration again starts increasing, and then we enter to the recovery zone, where the river is trying to recover back, is trying to reach to again its again trying to reach to the clean zone or natural conditions. So, in the recovery zone again you will see that the organic waste is will be further decomposed, okay, and the oxygen will start building up, and it reaches to a significant level. The fishes the fish population starts appearing, okay. So, those kind of things start coming in, and then water once like this by the end of recovery zone, and when it almost attains back the original dissolved oxygen or near saturation dissolved oxygen level, river enters again in the clean zone, and the conditions here will prevail back here. Okay. So, these are the four major zones: clean zone, decomposition zone, septic zone and recovery zone. Okay. Or if you are seeing from the introduction point of view, where the waste is getting introduced in the nature. So, then there is decomposition zone, where the decomposition start, septic zone the worst condition, the minimum dissolved oxygen, recovery zone, river again tries to get back to its like original state. So, tries to recover it, and then eventually it enters the clean zone, where it has received where it has attained its earlier pristine, near pristine stage. So, in clean zone, which it indicates that the it is your original DO is near its saturation value, the normal aquatic life is there in the river. However, particularly if your clean zone is coming after the waste introduction, if beyond this point there is no waste introduction, it is relatively better, but after this waste introduction, if you are in this clean zone, you can still like have some of the contaminants or some of the microbial impurities which have not been decomposed or which has not been degraded, they can still persist over here. So, it is not advised that way to directly consume this water if it is coming out of after it, if your point is in the downstream of the point where the waste has already been introduced. So, then one should avoid direct consumption of that water or the consumption of that water without proper treatment. Then in the decomposition zone, it will occur to a certain distance below the wastewater discharge point where it is introduced. It will be usually in the dark and turbid because a lot of waste is getting introduced. So, that immediate point one can see a color change also. There could be sludge deposits at the bottom because lot of solid materials and waste sludge also comes along with the water. So, they can get deposited in the water. DO is reduced significantly, okay, while CO2 increases, and which makes this zone as like more deoxygenative zone kind of thing. This zone is unfavorable for aquatic life, but certain fish species can still survive as we discussed. Then it enters septic zone where DO is minimum level and fish population are usually absent. There will be sludge bombs, mosquito, those kind of thing, and then eventually comes to the recovery zone where the water quality starts further improving. This water body tries to regain its original, the BOD degrades and DO rises. Okay. The organic matter is more or less is typically gets mineralized in this zone into the nitrate, sulfate, phosphate and carbonates, this kind of thing, and rest escapes in the form of CO2. The presence of algae become prominent. There could be protozoa, rotifers and other macroscopic plants can come. Okay. There are like microorganisms also, or organisms, small organisms can also come. The bottom will see the mussels and snails, all they can come at the bottom. So, that way the river is basically gets cleaner and cleaner as it moves ahead in the recovery zone, and post that, as we discussed, it comes again back to the clean zone. So, if we there are certain indices based on which we can assess the status of self-purification. Okay. So, as we say that river could be in the different zones or the different type of conditions it could be in. So, how do we know where what conditions is prevailing and what kind of what is the pollution level and which direction it is moving. So, that is typically done by the measurement, assessment or analysis of water with certain qualitative parameters, which are the usual indices for the self-purification. Okay. So, those quality parameters which are typically used, there are certain physical indices which are based on the color, turbidity and suspended solids. Okay. So, what is the color? Because if water is in a clean zone, we will see relatively transparent water, like not so dirty or polluted water. We will see the turbidity low, we will see the suspended solids very low, which eventually leads the turbidity. But if it is in the, let us say, decomposition zone, so as waste is getting introduced, you will see a much darker or dirtier color, increased turbidity, increased suspended solids. In septic zone, relatively we will see lesser suspended solids because they can get settled, but still there could be because of these microbial activities and all that, it is not going to be that transparent, and turbidity will be lower as opposed to the decomposition zone, but still it will be higher. Recovery zone, it tries to improve, and by the time it reaches clean zone, again it will attain a less turbidity, very less suspended solids and almost transparent color. There are chemical indices in the form of dissolved oxygen. What is the level of dissolved oxygen? And as we discussed, the dissolved oxygen varies. In clean zone, we will see the dissolved oxygen level near saturation value. In the septic zone, we will see the dissolved oxygen level very low, minimum less than around less than 2 or close to 2. In the decomposition zone, we will see that dissolved oxygen level falling, and in recovery zone, we will see that dissolved oxygen level increasing. BOD also, the very high BOD values, we are there in the sort of decomposition zone or septic zone. The lower BOD values, we are in the clean zone, okay. A very low value clean zone, or if it is getting further lowered, we are in the recovery zone that way. COD is a similar indicator of BOD. There could be dissolved solids, so that could be one of the chemical indices. What is happening to the metals, what is happening to the dissolved nutrients and those kind of stuff. Then there could be biological indices in the form of MPN. What is the we discussed this, what is the bacteriological pollution in the water, there that could be assessed in the colony forming unit or CFU as well. There we can specifically analyze selective macro and microorganisms to see the biological state of the water. Now, the DO deficit, if we see of a polluted stream, so as we were discussing earlier, the DO level initially falls and then builds up. Okay. So, if you see, let us say at any given point of time, if this is my saturation DO, which is 100%, okay, this scale is in terms of percentage. So, if this is my saturation DO, the dissolved oxygen level initially, or when the waste is getting introduced for say, is here. Okay. Now, if the dissolved oxygen level is here, so the difference, if this is my DO profile, okay, this is the existing dissolved oxygen concentration. Okay. So, if this line is my DO profile, let us say, so at any given point of time, the difference between the existing DO and the saturation value is called DO deficit or the oxygen deficit, right. So, when the water is having a DO value near saturation, we know that your DO deficit or oxygen deficit is very low. Okay. When it is in the septic zone, when your dissolved oxygen level is minimum, your DO deficit is maximum, okay, or we can call it critical, the DO deficit. Okay. So, that way we get the deficit of the dissolved oxygen in the river, right. Now, if my initial DO of the river is let us say here, and this is my saturation value 100%, my existing DO is here and waste is getting introduced at this point of time. So, obviously my DO level is going to fall as we discussed, and then it will touch a minimum and then start again sort of recovering. Now, this fall and gain is because of two distinguished processes. Okay. So, we discussed that the decrease in the dissolved oxygen is primarily because the organic matter is getting decomposed. So, BOD demands the oxygen, and that oxygen is getting supplied from the quota of the oxygen which is dissolved in the water, and as a result DO level in the water falls. So, the fall in the dissolved oxygen level is essentially because the BOD or the organic matter getting decomposed, and that is what this process is consuming oxygen or consuming the dissolved oxygen. So, this process is called deoxygenation process, and this you can see a deoxygenation curve here, okay, which says that you forget about the like DO profile at the moment, okay. you see if there is no dissolved oxygen coming in the system, right, if there is no dissolved oxygen coming in the system, then the profile of the dissolved oxygen would have been like this, because the this is because it is basically getting consumed by the process. The microorganisms are consuming oxygen for the purpose of oxidation of organic matter, and as a result the oxygen is getting consumed and your dissolved oxygen level is falling like this. However, your actual dissolved oxygen profile is like this and not like this, because there is another process which is re-oxygenation or re-aeration process, which sort of makes up for the oxygen deficit, and from the atmosphere the oxygen gets transferred into the water. So, this re-oxygenation will there is a at whatever re-oxygenation rate of the water is, based on that it will keep on adding oxygen in the water. So, there is one process which is making oxygen decrease, there is one process which is making oxygen increase. At any point summation of these two values will give you the total oxygen. So, initially it is here. Now, let us say at this point of time you are having this much of oxygen has been added, while this much of oxygen has been like from oxygen it has from initial point this much of oxygen has been consumed. Okay. So, this much oxygen consumed and this much oxygen added. So, this much consumed means still this much of remaining, and then thereafter this amount has been added. So, you shift this amount above over and above this, and you will get the true value of the dissolved oxygen level. Okay. So, you can try this at any point. So, let us say for this point, okay, this much oxygen is added. Okay. So, let us you say that DO added, and this much oxygen is still remaining in the system. So, this is your DO remaining. Now, this much is added and this much is already remaining. So, you add the remaining DO remaining over here, and you will get to the value of the actual dissolved oxygen. So, this oxygen sag curve this oxygen profile or the oxygen curve or DO profile, which is also called as oxygen sag curve, because there is a sag is coming. If you see this curve, so you can clearly see that there is a sag in this profile, and that is why this is called oxygen sag curve or DO sag curve. Okay. So, the DO curve or DO profile or DO sag curve is actually the sum of deoxygenation and re-oxygenation profiles. Okay. So, what is the deoxygenation and re-oxygenation? You add these two and one is going to get the oxygen curve. So, this oxygen deficit at any time in a polluted river body will be defined as saturation DO minus actual DO. What is the saturation dissolved oxygen level and what is the actual dissolved oxygen level, and the gap between that is called oxygen deficit. So, like this is oxygen deficit at time t. This is the critical oxygen deficit when the oxygen level has fall to the minimum. So, the deficit becomes maximum, and this is the initial oxygen deficit at time 0. So, when you started, this is at time 0, this is the deficit in the oxygen. So, this can also be estimated by identifying the different rates of oxygenation and re-oxygenation curve, and for water body to be clean the oxygen deficit has to be near 0. So, as good the oxygen dissolved oxygen level is there in the water, that indicates that there is not much of dissolved organic impurities present in the water or dissolved organic carbon present in the water, and that makes that sort of kindly gives an indication that the water or the river is in good state, okay, or is not very much polluted, because if there is too much of organic pollution, it will consume the dissolved oxygen and the DO level will fall. So, a good healthy DO level, a DO level near saturation indirectly indicates that river is nearly clean, particularly in terms of the organic contaminant. It could be still polluted by the metals or by the heavy metals, other things which does not consume oxygen, but it is relatively clean from the oxygen consuming contaminants. Okay. So, as we said that there is deoxygenation and re-oxygenation, the two processes which in combination gives us the dissolved oxygen profile. So, the DO content of a polluted water body goes on reducing with the breakdown of organic matter, which is the deoxygenation process, and that can be seen by this expression typically. So, if L is the organic matter present or BOD present LT, so rate of change of the BOD is actually proportional to the KD times LT existing BOD. So, this is a simple first order expression, okay. Or we can say that rate of change of BOD is proportional to the existing BOD, okay, which makes it the first order, and here or because it is decreasing, so proportional to the minus of this thing, and if we add a proportionality constant, so this expression becomes like this. Now, here KD is the BOD reaction rate constant, how BOD is decreasing, right. So, that is what KD is. KD is called BOD reaction rate constant, but we know that the rate of the like organic matter decomposition, the bacteria utilizes dissolved oxygen for organic matter decomposition. So, the consumption of dissolved oxygen, how much dissolved oxygen is getting consumed in the process will be proportional to the amount of organic matter which is being degraded. So, more amount of organic matter being degraded, more is the consumption of organic matter, right. So, that way actually the rate at which the oxygen gets consumed or rate at which the BOD gets degraded is the same rate at which oxygen gets consumed, and that is why we know that the rate of oxygen consumption we earlier discussed is the deoxygenation process, and this rate is called deoxygenation coefficient or deoxygenation constant also. So, KD is either will be referred as BOD reaction rate constant, which is same as the deoxygenation constant or deoxygenation coefficient, and it is a it depends on the nature of organic matter and what is the existing temperature, based on that it depends, okay. And it is a simple first order expression. So, we can solve this, eventually you will get LT is equal to L0, which is initial BOD into L0 to e to the power minus KD times T. This is standard solution of this expression, okay. So, that way we can get the BOD at any given point of time, that is how the BOD gets degraded, okay. So, that is the deoxygenation part, and then we have the re-oxygenation part, which is a process by which the atmosphere supplies oxygen to the water body, and its rate will depend on the oxygen deficit. So, it is typically proportional to the deficit of oxygen, because if you are having a river with the, let us say your saturation dissolved oxygen is 9, okay, 9 is your saturation value and your existing DO is 8 milligram per liter. So, your DO deficit is 1. Now, your oxygen level, if you see, could actually existing oxygen level is here, the maximum oxygen level could actually be there. So, there is very little deficit and your rate will be very slow, because rate is proportional to this deficit also. So, rate is going to be very slow. However, if you are having a river system where this saturation level means it could attain like this and your existing level is very low. So, you are having a good enough deficit, and then the rate will be very high, the rate of oxygen transfer will be relatively very high. So, it is actually directly proportional to the deficit, okay. Then depth of the receiving water body, it decreases with increasing depth. If your depth of water body is high, so the rate of oxygen transfer, particularly the lower stratas, will be very low. The condition of water body, of course, a running stream will have more turbulence and more re-oxygenation than a static pond or quiescent stream, and what is the temperature of water, because our saturation DO depends on the existing temperature of the water bodies. So, that way it will be basically function of these things. Now, the DO deficit is presented through a very popular equation which is typically known as the Streeter-Phelps equation, okay. And this is the Streeter-Phelps equation is the one which like gives us the profile of DO. So, the DO sag curve you saw earlier can actually mathematically represented through this equation, which is called the DO deficit equation or the Streeter-Phelps equation. Okay. So, the equation is that DO deficit at any given point of time t, here D is the deficit. So, DO deficit at any given point t is equal to Kd into L0 minus Kr by Kr minus Kd, and e to the power minus Kdt minus e to the power Krt and d0 e to the power minus Krt. So, here your dt is the DO deficit at any point t, at any given point of time t. L0 is the ultimate first stage BOD of the mix after the point waste is mixed. So, if this is my river, I am having a sorry. So, I am having a waste stream coming in over here. So, after this point, what is the my ultimate BOD is actually L0. So, ultimate BOD is an estimate of the organic matter. So, what is the total amount of organic matter present, okay, because that is an estimate of the ultimate BOD. So, total amount of organic matter present or the ultimate BOD at this point. D0 is my initial oxygen deficit. So, what is the dissolved oxygen level at this point of time? So, if dissolved oxygen level is let us say DO 0, so D0 is actually the DO saturation minus DO 0. So, that becomes my D0 or the initial oxygen deficit, and Kd and K are the deoxygenation and re-oxygenation coefficients. Okay. So, Kd, which is the deoxygenation or the BOD rate constant, the typical values are 0.1 to 0.2, okay, at 20 degrees Celsius, and at other temperatures we can estimate following this expression. So, at Kd at any temperature is Kd at 20 degree to the power 1.047 T minus 20 in degree Celsius, okay, where T is in the here T is temperature in degree Celsius. Similarly, Kr is the re-oxygenation rate, and this typically can be determined using this equation at 20 degrees Celsius, where V is the velocity and Y is the average stream depth, okay. And for other temperatures similar to this, we can use this expression for determining the Kr at other temperatures. So, once we know that, once we have an estimate of Kd and Kr, and we know what is the ultimate BOD or the total amount of waste which is being added to that, we can estimate what will be the deficit at any given point of time. Okay. So, knowing the amount of BOD and these two different rates, we can predict the profile of the dissolved oxygen, and the profile of the BOD prediction is also same and simple. So, as we discussed, the profile of BOD is equal to L0 e to the power minus Kd into T. So, this expression, this simple first order expression will give us the profile of the BOD or profile of the organic matter present in the system, while the Streeter-Phelps equation will give us the profile of the dissolved oxygen or dissolved oxygen deficit, DO deficit, which eventually can be taken as the profile of dissolved oxygen as well. Okay. So, that is how these two are determined, and then we let us conclude these discussions here only, and in the next class we will again discuss the further integrities of how this works and how we can get the minimum and maximum, the minimum DO level in a river water and how far it is going to arrive, the estimates of those. Thank you.